To give us some idea what we're talking about, table of boiling point fractions for hydrocarbons. Now we won't only be talking about hydrocarbons today, but this is a good indication of what we're talking about. Of the hydrocarbons C1 to C5, so methane up to pentane, we're talking about boiling points ranging from minus 161 degrees Celsius up to plus 36 degrees Celsius. That's also the range that very often gases and other volatile compounds need to be analyzed. Now, that is not as easy as it sounds, mainly because all of these light boilers have very low retention on traditional liquid phase capillaries. Now, the vast majority of GC applications are performed on liquid phase columns, the so-called wall-coated open tubulars, or WCOTs in short. Most of us are quite familiar with those WCOT separations. I estimate they cover about 95% of all analysis. All polysiloxane and polyethylene glycol liquid phases fall into this category. In essence, these kind of separations are based on a gas-liquid partitioning mechanism. Solute, our compound of interest, distributes itself between the moving gas phase and the stationary liquid phase. That distribution is defined by the affinity of the analyte for the liquid stationary phase, but also by its volatility. Now, the difficulty of using liquid phases for the separation of gaseous solutes is that they are so volatile, they prefer the mobile phase over the liquid phase. As a result, the partitioning coefficient is low, the compound retention is minimal, and therefore the separation is incomplete. Or in cases there's no separation at all. Let me show you an example. Now, this is a good illustration of the limitations of wall-coated capillaries for the analysis of volatiles. The column is a dB petro. It's a non-polar column for the detailed separation of hydrocarbons. It's 100 meters long and it's a narrow bore of 0.25 mm internal diameter. About 350,000 theoretical plates. There's obviously no shortage of efficiency. We also apply cryogenic cooling for this analysis of ethylene, and the oven program starts at minus 40 degrees. Got just some level of retention for these compounds. As you can see, the column is unable to separate the C2 isomers, and actually it also can't separate C3s. So plates alone are not enough. We need a column with better selectivity, and possibly with more retention as well. That's where plot columns come in. The same analysis now, but on an alumina-based plot column. We've got an excellent separation of the C2s, of the C3s, and also of the C4 impurities in the ethylene. The column is just 50 meters long, and it's a megabore of 0.53 millimeters ID. We don't need to use cryogenic cooling, as the initial temperature starts at 35 degrees Celsius, and the program runs up to 190. So what is a plot column? Plot columns have a layer of porous particles on the inside wall of the capillary. It is this layer of particles that act as the stationary phase. The manufacturing of plot columns is somewhat different from liquid phase columns, but you must imagine that these particles are deposited on the wall from a suspension. The separation on plot columns is based on a different interaction mechanism compared to liquid phase columns. For gas-liquid chromatography, it's the difference of solubility of the analytes in the liquid phase that drives the separation. Plots is the difference in analyte distribution between carrier gas and the particle adsorbents. It is gas-solid chromatography, and its behavior is different. The advantages of gas-solid chromatography are usually an improved selectivity and an improved retention of highly volatile solutes. Both factors drive the improvement of the separation. We can distinguish two main interaction mechanisms for plot columns. One is based on shape and size, and the other on surface interactions. A good example of materials that rely on shape or size interactions are zeolites or molecular sieves, and are used often for the separations of permanent gases. Repulsive 5A is a good example, but also porous carbon serves as a shape selector. Adsorbents that mainly function on their surface interactions are, for instance, alumina and silica. The diagram is not to be interpreted as an absolute, it's just a general guideline. Usually there's a mixture of the two interactions that are occurring. However, alumina columns tend to exhibit mostly surface interactions, while molecular sieve mostly size-shape interactions. And in between, there are the porous polymer adsorbents that exhibit both types of interactions. What are the advantages of plot columns? Basically three. It's the retention they offer, the variety of available adsorbents, and they have the efficiency of a true capillary. High retention for volatiles mean that cryogenics are not needed, and that also makes plot columns suitable for multi-column setups with fast switching and hard-cutting techniques. There are numerous analyzers for the petrochemical industry based on plot columns, just because of these reasons. There are many adsorbents that can be coded as a plot, and that means that you can target certain analytical requirements that you may have by selecting specific plot columns. We will go through them later in the webinar. Now, plot columns have displaced packed columns in many applications for predominantly gases, hydrocarbons and volatiles. That's primarily because of the high efficiency and the separation power that they offer. But there are still quite a few specific applications where packed columns are still the preferred option, particularly in the gas analysis sector. They're virtually unbreakable and very robust, with a high degree of safety that's required for process analyzers. It's possible to get them in a very tight space, and they also have a far higher sample capacity in a plot. So packed columns are here to stay for sure. There are some limitations and things to consider when working. Number one, they have a lower sample capacity than what you would see for a thick film wall-coated open tubular, certainly for a packed column. That's why it's often advised to select a megabore plot column version, 0.53 mm. That's to get the highest possible loadability out of the plot column. They also have a limited dynamic temperature range, more limited than siloxane liquid phases, for instance. That restricts their overall analytical scope. Certain larger, higher volume compounds just will not elute because of that. Adsorbents can be highly active, so certain components will stick and either not elute at all or take excessive conditioning to do so. You might need to take some mitigating measures to make the plot columns run smoothly in those cases. A pre-column setup, for instance. Number 4. The upper temperature limits for the columns are there for good reasons. If you exceed them, it's possible to face selectivity changes due to the particles undergoing some molecular rearrangements. Stick to the maximum allowable operating temperature is the message. They are made of particles that are stuck together, and they stick to the wall of the tube. But if treated in a manner that causes the particles to break free from the bulk stationary phase matrix, the particles will fly through the column. Vector or gas switching valves. There are, however, solutions to fix these potential issues. Despite these drawbacks, plot columns are popular. Separation solutions for many applications. Here we have an overview of all the plot columns in the Adjunct GC column portfolio. It's quite a selection, and that's partly because of the merger of HP, J&W and the Chromatogram portfolios. Put a red box around the alumina and porous polymer column. They are by far the most popular plot columns. Alumina is used for hydrocarbon separations, and there are a number of different selectivity options there. Polymers, there are the non-polar Qs and the polar U versions. Zeolites, silica and graphitized carbons are the other column category. And down on the left, the CP-Loox and the oxy plot. These are the plots for the analysis of oxygenates. We'll quickly go through the type of plot columns and the analysis, the separations they're used for. Permanent gas analysis, noble gases included, can only be separated efficiently using mole-sieve or zeolite columns. The select permanent gas column is a combination of two columns, with one of them being the mole-sieve type. Put a red flag on CO2, carbon dioxide. It's always the compound that spoils the separation party on the mole-sieve column, as it absorbs on the mole-sieve material and it requires proper high temperature conditioning to remove it. Light hydrocarbon analysis is mainly the domain of the alumina columns, which have an unparalleled separation for the hydrocarbon isomers. Porous silica, porous polymer and carbon columns supplement the alumina in this field, sometimes used for specific hydrocarbon separations. Sulfur components are always an analytical challenge because of the plot columns for sulfurs would include the select low sulfur, but also the gas pro, silica plot, and the porous polymers. Oxygenate analysis in the petrochemical industry, like for alcohols and ethers, can be performed on special columns, like the OX and the oxyplot. The separation versatility of the porous polymer columns is illustrated by its use in so many different types of analysis, including solvents. The porobond Q would be an excellent choice here. CFCs finally. These compounds, often very volatile, are analyzed with porous silica, the gas pro or the silica plot columns. Porous polymer plot columns are arguably the most versatile, and you could use them for the separations of hydrocarbons, solvents, oxygenates, gases, and CFCs. They are also special as it is possible to inject samples with high concentrations of water on them. Most other plot columns have an issue with that. It's even possible to quantify water on the more polar U-types. There are three versions. The Q-type is the most apolar one and is based on a styrene DVB polymer. And there's the polar U-type, based on a styrene glycol methacrylate copolymer. Then there's also a mid-polar S-type, but that is actually hardly ever used. What are these polymer plots used for and what are their limitations? The Q-porous polymer plot is often used for straightforward ethane, ethylene and propane-propylene separations. In percent levels, I mean. They are not suitable for impurity analysis in ethylene and propylene. Hydrogen sulfide and carbonyl sulfide are key components of interest in the analysis of refinery gas, usually from 1 ppm up to low percent level. Now porous polymers can't go below 100 ppm for H2S as it absorbs at these lower levels and strong tailing can be observed on the peaks. The Q is often used as a pre-column for the emulsive column, as that one is used for permanent gas separations. They're quite poor in separating C4 hydrocarbon isomers, however, so alumina is the go-to column there. Their compound elution and selectivity is not sensitive to moisture, either when it's present in the sample or in the carrier gas. This is an example of a refinery fuel gas separation, using an HP plot Q column as the pre-column to capture the permanent gases, which are then transferred to the emulsive 5A column for further separation. The HP plot Q provides the bulk of the analysis with the separation of CO2, H2S, water. You can recognize the water peak by its tailing, its peak number 8, methanol, and then the separation of the C2s, C3s, C4s, and also some C5s. And that all within 12 minutes. It really illustrates the versatility of these porous polymer plot columns. I've already mentioned porous polymer GC columns can withstand water quite well. In this slide you can see the effect of splitless injection of 25 microliters of water. In total 5 injections were made. The elution of methanol, acetonitrile, remains totally unchanged. The analysis is performed at 80 degrees Celsius, so it's even possible that the injected water condensed on the column itself, but no adverse effects can be seen. It means that samples with an aqueous matrix can be analyzed confidently. These plot Q columns are quite robust. The porous polymer plot Q and HP plot Q have been tremendously popular since they were introduced in the 1980s. These columns, however, have some characteristics which are a little bit less desirable. A potential particle loss is one of them. Unstable baselines and detector spiking can be the result, and a change of technology was needed. Agent is the inventor of the exclusive bond technology for plot. Technology has been applied to carbon and porous polymer plots. While previously the porous layer consisted of billions of tiny stacked particles, the bond technology created an in situ layer inside the capillary. The capillary is in essence the reaction vessel. The images illustrate the significant differences in the build-up of the layers. Separate particles can clearly be visible for the columns like the poroplot Q and HP plot. Columns may lose some particles during use, especially resulting from pressure shocks or vibration, and they require so-called particle traps on the detector side of the columns to capture any dislodged particles. Traps are short 2-meter columns, coated with a non-polar liquid phase, and it's coupled to the column by a press-fit connector. Bond columns are far more mechanically stable, so nearly no particle shedding occurs, although it's not absent. Now the value of porobond columns are not only limited to a better stability. We'll see that in the next slide. The analysis of solvent is often performed on a 6-4 type liquid phase column. This chromatogram illustrates how it can be done on a porobond Q. It takes about 27 minutes and the oven program goes up to 300 degrees Celsius. That's a remarkably high temperature for a porous polymer GC column. As you can see, there are excellent peak shapes for polar compounds like ethanol. It's an excellent analysis. I've mentioned the issues with particle release from that bond technology was one of the solutions, although not perfect. To eliminate the issue once and for all, I then developed the integrated particle trap technology. In this picture you can see how it looks. On either side of the analytical column a particle trap can be found, but there are no connectors anymore. With the particle traps on two ends of the column, this provides absolute assurance and safety for valves and detectors in both fore and backflush modes. Again, a solvent analysis on the porobond Q column, but now it has an integrated particle trap attached. Excellent peak shape performance for all components. The effect of the particle trap on the separation itself is minimal. A number of interesting observations. There's a fairly decent separation between meta and pyroxylene. That's not. The other thing which is interesting is the peak shape for peak number 18, which is MTBE. Now this effect of broadening is fairly common for components that have a quite spherical structure of the molecule. MTBE is a good example, but you can also observe a similar effect on peak number 22, that is 1,1-trichloroethane. It's suspected that these analytes are affected by additional interaction mechanisms based on shape. Just to clarify, there's absolutely nothing wrong with the column itself. It's a perfectly good column. This is an interesting overview of the selectivity of the three poroplot polarities, Q, S and U. We're analyzing C1 to C3 isomers. On the Q version, ethane and ethylene are well separated, as well as the propane-propylene pair. Acetylene coalutes with ethylene. On the polar end of the spectrum is poroplot U. Good separation of the C2 isomers, but unfortunately propane and propylene now coalute. The S version sits right in the middle with its selectivity. The separation of propane-propylene is just not as good as on the Q. That brings us to alumina plot columns. Popular for separations of light hydrocarbons, and I would say probably the best choice. Generally for C1 to C6 hydrocarbon separations, but you could extend this to C9 in cases. Applications include natural gas analysis plus ethylene, propylene and butylene streams. Impurity analysis mainly. There are some applications for environmental hydrocarbon distributions in urban air. The elution follows a pattern of alkane, alkene, alkyne. So the more unsaturated the hydrocarbon, the more retention, the lesser the elution. Alumina is very active. It requires deactivation to become usable as an adsorbent for gas chromatography. In the early development days of the alumina column, they were deactivated with a copper sulfate moisture filter. Not a stable deactivation or process, so that was quickly abandoned for a deactivation using salts. Potassium chloride and sodium sulfate are the most used, but there are also some proprietary deactivations in the market. My red flag is back. Watch out for moisture in the carrier gas and in the sample. Water is a deactivating agent on alumina we've seen, so its presence affects retention and selectivity. Be careful. Use proper moisture filters in the carrier gas. Gas cleaning filters are recommended. What's the difference between a potassium chloride and a sodium sulfate deactivation? This comparison chromatogram illustrates what's happening. Generally speaking, the sodium sulfate version provides more retention for unsaturated hydrocarbons, and that results in selectivity differences and an alternative elution profile. A good example is how acetylene switches position in front of isobutane and normal butane on potassium chloride to behind them on sodium sulfate. What are the implications? Now, potassium chloride is an excellent choice for the analysis of impurities in ethylene, propylene, and also in 1,3-butadiene. The sodium sulfate version is the better choice in case of the analysis of C4-butylene feeds. Something to bear in mind is that for unsaturated compounds, the alumina columns tend to show overload more quickly. You can see that at closer inspection of the chromatograms. It may have an impact on the separation of close eluting components. This is how overload on alumina looks like. It's the analysis of impurities in butadiene. Now the matrix butadiene is obviously present in high amounts, and therefore its peak shows an overload profile. It looks like a triangle with an almost 90-degree angle at the front and some sort of tail at the back end. The reverse of an overload profile on a liquid phase type column. This chromatogram also illustrates why you should choose one or the other deactivation. Here we have opted for potassium chloride. Because of that choice, methyl acetylene elutes just in front of the massive butadiene peak. Chosen for sodium sulfate, that same methyl acetylene peak would have been on the tail of the butadiene because of the different selectivity, and it would have been quite hard to quantify as a result of that. Alumina columns are not perfect. They are moisture sensitive to begin with, but there is also partial irreversible absorption of highly unsaturated hydrocarbons occurring. This was the reason for the introduction of the so-called MAPD version, an alumina column with a higher degree of deactivation which provides a higher response for these type of unsaturates. This graph clearly illustrates that for propadiene and methyl acetylene. But even so, the recovery for them will never be 100%, and this means that an analysis using an alumina column always requires an external standard. It's never possible to rely on a 100% level calibration, as these highly unsaturated components will then be underreported. Alternatives for alumina as the light hydrocarbon column are the silica-based ones. They also have an extended hydrocarbon range compared to other plots. These silica columns are inert enough to be able to analyze low ppm levels of light sulfurs, such as hydrogen sulfide, COS, and the mercaptans. Very stable particle layer makes them compatible with MS detectors. They're also not sensitive to moisture in the carrier gas, which is definitely an advantage over alumina. This is the result of a monomolecular layer of water present on the silica surface already. And that layer of water is released above 200 degrees Celsius. This explains the maximum temperature of those silica-based columns. So how does a porous silica-based plot column perform for hydrocarbon separations? In this slide we see an example of that. It's the analysis of propylene, and you can see the matrix clearly here right in the middle. Riding on the tail of the propylene are iso and normal butane. Not easy to quantify because of the tail. Have a closer look at the elution of cyclopropane. It's there well in front of the large propylene peak and clearly separated. That's just not possible on alumina. The silica plot column provides definitely an alternative selectivity for C2 and C3 hydrocarbon separations in comparison to alumina plot. and it can benefit some specific requirements. The quantification of cyclopropane could be one of them. Now, the separation of the unsaturated C4s is just not very good. Porous silica columns are not the best separation choice for that group, unfortunately. The Porobond Q was part of the development of the bond technology that I covered earlier in the webinar. The high temperature capabilities of the Porobond column allowed the development of a novel solution for the analysis of permanent gases, CO2 and the C2 hydrocarbons, based on two columns running in parallel. A MOLSI-5A for the separation of the permanent gases, including carbon monoxide, and a second column, a Porobond Q, for the elution of CO2 and the C2s. Here in the top right you can see how that two-column setup looks like. So what happens is that the injected sample is split over the two columns, with the gas stream joining each other again at the exit and then going into the thermal conductivity detector. The entire separation takes about 10 minutes. The dimensions are optimized to avoid any interfering elution of components and to produce a fast analysis. Why is the Porobond Q pivotal to this solution? Because CO2 is also injected on the MOLSIF column. That requires a bakeout after some time when it loses its separation efficiency because of the CO2 absorption. A bakeout at 300 degrees Celsius restores the MOLSIF separation performance. Only the Porobond Q that's able to withstand that temperature without any loss of performance. And that brings me to the analysis of oxygenates in the petrochemical industry. That analysis basically splits into two parts. First, there are the oxygenates that are blended into the gasoline. These are additives that boost the octane content, improve combustion and the performance of the engine, preventing the knocking effect. MTBE, ETBE and ethanol are examples of these additives. They're present in percent levels, and the analysis is usually performed on wax or very polar liquid phase columns like TCEP. The other oxygenate analysis deals with their presence in intermediates, monomer naphthas. The presence of oxygenates has a poisoning effect on the catalyst, which will lower the yield. High costs and more refinery downtime are the result of that. These are expensive, so monitoring the presence of ppm levels of oxygenates is critical for an effective refinery operation and also relates to pricing for the intermediate products. The analytical GC solutions are different, and they rely on two very specialized adjunct columns, the Low-Ox and the Oxyplot. Both of these columns are based on a very special stationary phase. This material has a very low analyte capacity, but as we are only interested in ppm levels, this doesn't present an issue. It's the very high selectivity for oxygenates in comparison to the hydrocarbons which does the trick. Both the Oxyplot and the Low-Ox exploit this. It is well illustrated in discriminant which runs on the Low-Ox. On the left you find the elution of the hydrocarbons, in this case C6 to C12, and on the right are the oxygenates. Basically, the Low-Ox produces a clear-cut separation between hydrocarbons. There will be some elution overlap for the late eluting hydrocarbons, the very light ethers, but this can easily be resolved with the use of a non-polar pre-column and some basic valve switching. And this is the resulting chromatogram, an oxygenate analysis of naphtha with a dB1 pre-column and an oxyplot. After elution of the oxygenates onto the oxyplot, the higher boiling hydrocarbons are backflashed from the dB1, leaving a clean stretch for the oxygenates. The first eluting one is dimethyl ether, and the last eluting are usually some C5C6 alcohols. Note that the Low-Ox and the Oxyplot are only available in a 0.53 mm megabore format. That brings me to the very last plot column that I'll cover in this webinar. Again, a special one. The Select Low Sulfur. It's based on a super permeable and porous stationary phase. It's a proprietary material. Quite a unique characteristic that it has in terms of separation of volatile sulfur components and light hydrocarbons. And it's because of that it avoids quenching phenomena on sulfur-specific detectors. especially when analyzing propane and propylene matrices. It's highly inert and there's no absorption of volatile sulfurs like hydrogen sulfide and methyl. And that allows for the quantification of H2S in particular at very, very low ppb levels. It comes as one part number only. Although it is a plot column, or it behaves as one, there's absolutely zero loss of particles for this column, and it's compatible with all sulfur-specific detectors. And this is the very last chromatogram of the webinar. And here you can see the analysis of hydrogen sulfide and carbonyl sulfide in propylene. We can see the quenching of the PFPD detector right here at this spot, but it doesn't interfere with the quantification of particularly COS. Another thing to note is that the response for both H2S and COS is identical, and that indicates that H2S is not adsorbed at all on this column. It provides a perfect reliable quantification of H2S even at the lowest ppb levels. And finally, some considerations and my recommendations. Consider the elution pattern and selectivity. It's always better to elute a minor analyte in front of a matrix peak due to tailing associated with overload. The capacity of plot columns is lower than of liquid phase columns. Larger internal diameter columns have a better capacity, so consider using 0.53 mm columns. The inertness can be an issue for active analytes. We've seen that. For example, ppb sulfur analysis is just not possible on porous polymers, but works very well on gas pro. Consider the temperature limits of columns with respect to what else is in the oven if you're using multiple columns. Then something about column contamination. Plot columns are very retentive, so impurities in the carrier gas stream or contaminants in the inlet will focus on the head of the column and create problems. If those heavy analytes are not eluted from the column during run, they will elute later on as blobs. Consider what other components are in your sample. Is there a lot of water, CO2, higher molecular weight hydrocarbons? Column selection and system setup will depend upon the composition of the entire sample stream, even if these other components are just not important for you. And on a very last note, always install proper moisture filters in the carrier gas when working with plot columns. It's really essential. Thank you very much for your attention today.